Hi there, Clifton. I believe you're on mute.
Hello, welcome to the final installment for the year 2021 of the Construction History Society of America webinar series titled Structure and Materials and Other Tales of Construction History. I'm one of the moderators. My name is Clifton Fordham. I'm also one of the co-hosts. The other co-host is Marisa Gomez Nordijk. You'll be seeing her soon. The panelists are Jenna Bressler, Associate at Silman, Vida Pivo, Associate Professor at the University of Michigan, and Rachel Cruz, who's a building safety scientist for health and safety and a health and safety executive. Next slide, please. Before we get started, I would like to bring our attention to two upcoming events. The first, I'd like to let you know about our membership. We encourage professionals, academics, independent researchers, and students to join. It's a great community. We have a conference coming up. We receive journal publications, and there's also a newsletter. The membership dues for an individual are $75. Corporate and institutional contributors, the fee is $250. Sustaining members, $125, and students, a modest fee of $25. Again, the upcoming events, our spring webinar series will conclude on the 21st, conclude. And so look forward to that. Please put on your calendars. And our upcoming conference, Quarrying History. It'll be held at Kennesaw State University in Atlanta from June 2nd to June 4th. If you're interested in submitting an abstract, the deadline coming up is January 3rd, beginning next year. You can visit our website, www.constructionhistorysociety.org, or the conference website, as you see on this slide. I'll actually post those in our chat box. I'd also like to tell everybody that if you could please mute, it'd be appreciated. If you are using the chat box, we would hope to limit that to questions to our panelists. If you have to communicate with a fellow, someone that you want to say hello to, please direct that message directly to those individuals. And also, I'd like to let you know that this is being recorded. On that note, Marisa. Oh, one more point. We're going to try to allow for some question and answers after each presentation, but for some reason we're running behind. We'll defer those questions to the end of the conversation.
One moment. Excuse me, just one moment. Thank you, everyone. Our first speaker is Jenna Bressler. Jenna is a preservation engineer. She holds an MS in historic preservation from the University of Pennsylvania and is currently project manager for the renovation of Michigan Central Station in Detroit. Her presentation is entitled Gordon Hall, Investigations of a Marble-Clad Facade. Jenna, I will hand it over to you.
Hello, everyone. Sorry about that. I was trying to figure out how to unmute. Everything gets minimized when you're sharing your screen. So My name is Jenna Bressler, as Marisa said. I'm a structural engineer and I specialize in historic preservation. And I want to thank everyone for coming today to hear me and the other two lovely panelists to present some of our research and work. I also want to thank the Construction History Society of America for inviting me to speak today. Very excited. I am very excited whenever I get a chance to meet with this group. It's a great group and of professionals and historians and academics. I also, before I begin on my talk on Gordon Hall, I want to thank two other key players in this project. I want to thank Harvard Medical School for having the patience, understanding, and commitment to allow the level of investigation and discovery that we needed to complete, and that I will talk about in the coming slides for fixing the building. I also want to thank the architects McGinley Kelso Associates in Boston, Massachusetts, who were the architects and prime consultant for the work. So Gordon Hall is one of 5 buildings designed in 1906 by the historic firm Shepley Rattan Coolidge Architects, and is part of Harvard Medical School's main quadrangle off of Longwood Avenue in downtown Boston, which is what you see on the close-up image on the right. So on the left shows you just an overall understanding of Boston in the Massachusetts area. Harvard Medical School is in the southwest region of Boston proper. And actually, if you Google search Harvard Medical School, the dot from Google Maps lands directly over Gordon Hall. So as you can see, it is at the southern end of the main quadrangle with the other 4 buildings on the sides of the quadrangle. All 5 buildings consist of thick marble and brick masonry exterior bearing walls, with steel frame that you can see in these images as the interior makeup. So the steel framing is supported on exterior steel columns as well that are clad in brick, and then the final cladding is marble. The stone cladding is a Vermont marble of the Dorset Plateau Quarry, and that will be of interest in coming slides. So Gordon Hall is the flagship building at the head of the quad. The building has large porticos on the north and south elevations, each supported by 6 large marble-clad columns. The buildings were originally designed with exposed brick facades, but the story that's been passed down in the history of the building is that the contractors on this job were the same contractors working at the New York Public Library. And the marble that was being quarried in Vermont was coming to New York in such a variety in color and texture that the New York Public Library were rejecting most of the stones, and stockpiles of stone was just being left and not being used. So the contractors who were building Gordon Hall and the other buildings around the quadrangle at the same time suggested to Shepley's team that they should consider changing up their design and cladding the buildings in marble since they had all of this excess stone. And they did last minute design change from a brick exterior to a stone cladding. And today that varied color is a trademark of the buildings loved by its patrons and the surrounding community. So our project began when the medical school invited McGinley Kelso Associates to do a facade assessment of Gordon Hall as they were finding areas of stone damage, cracking, spalling, and staining around different areas of the building. The architects called in us, Silman, to perform structural investigations on isolated facades. Isolated facade conditions that appeared to be structural in nature. So they wanted our opinion on what we thought was going wrong and how best to fix them. So the 3 specific areas I will discuss in this presentation are 1, the building corners and returns, 2, the Ionic style volutes that the lift is near in this image at the tops of the columns, and 3, the entablature solvent stones that span between those volutes. As I said previously, the building is clad in a Dorset Vermont marble, which is a very soft and porous metamorphic stone with integral networks of veins that, as we'll see in coming slides, they don't hold up well to water and exterior elements if they're improperly detailed. So the first area we looked at the building corners, we saw full height vertical cracking through the stonework, practically at all building corners. The lengths varied, but their distance from the building edges were uniformed, and they seemed to be aligned with the stone jointing of the coursing above and below where the cracks were forming. So to understand what was going on behind this, we conducted a probe and pulled out one of the cornerstones. And what we found was, for the most part, the building stones were about 8 to 9 inches thick around the majority of the building, but at the ends, they thinned them up to 4 inches. And that was most likely to lap around the thickened corners of the building that accommodated steel columns and the brick encasement around those steel columns. So they had to thin up the stone. So we determined that this vertical cracking was due to thermal movement of the masonry interior that caused an internal pressure behind this stone cladding that was thinned up around these edges. This particular marble expands 75% more than traditional brick masonry, something that the building designers would have needed to account for in their detailing. With nowhere to alleviate the pressure, and given the thin profile and the long spans at these corner stones, the stone wanted to crack. So the cracking was the building's way of relieving that pressure, and the repair that we implemented needed to account for this. So we replaced the cracked stones with new stones and installed the desired vertical jointing with a soft tooth joint in these areas to allow for the thermal movement in the future without additional cracking. So up close review of other areas revealed fractions, spalls, and cracking, mostly at the decorative projections, the cornice lines, the dentils beneath the cornice, and the parapets. We worked with Chalmette Construction to remove large areas of imminent spalls while on the lift. Entire horizontal sections of dentils and cornice sections were able to be removed. Removal of some small spalls revealed the presence of rusted stone anchors or cramps that were installed too close to the exterior. Other areas showed spalls aligning with the inherent veining in the stonework and avenues where the stone was most susceptible to freeze thaw. Here are more conditions we saw up close via a lift. So you could see some exposed steel elements were clearly rusted in close proximity to the exterior edge of the stone, and that was building up some pressures behind the stone, causing cracks that we saw at vertical jointing and horizontal projections. The next area we focused on were the column volutes. So the 6 north and south column capitals are decorative ionic scrolls, also known as volutes, and they're made of solid marble. They support large entablature elements spanning between the columns. The columns support the entablatures and the roof, decorative cornice, and parapet overhead. Because of this stacked construction, a significant amount of load is going to these columns. Extensive cracking was seen over and between every column. Close-up review showed that most of the volutes were already patched with a buff color and netted. Even closer review showed large cracking through significant chunks of the volutes, probably why the netting was installed. But also you could see around the decorative elements of the volutes were these metal straps that were installed at some point in the building's history. And those were a means of an additional reinforcement should large scale volute cracking lead to spalling. So we wanted to begin kind of understanding the scope of repairs that were needed. And so we began with a full documentation of the project. We began by performing a point cloud scanning of the entire building facade. This allowed us to take measure of the baseline current state of the building and allowed us to look at the plumbness of the elements. And also, as we'll see in the next slides, it helped us detail and document the repairs to the decorative features like the volutes. From our point cloud and our on-site assessment, we developed drawings to document each column capital as seen on the screen now. We developed itemized drawings to document exactly how much of each column capital needed replacement, and our point cloud model allowed us to illustrate those sections and detail their installation. With these drawings, the stonemasons were able to create mock-ups of repair areas in plaster molds first to recreate a perfect match to the existing elements in their decoration. The process of recreating sections of the column capitals took place off-site. Giant blocks of marbles from a Vermont quarry not too far from where the original stone was taken were cut by means of a water jet blade in the general shapes. From there, a CNC machine began to carve in the decoration. The general shape and decorative projections were machine carved, but once we got to the more intricate detailing, those were done by hand, by skilled masons. And so here are a couple of images of some of the completed decoration. So now back to the metal straps. The school believed that these straps were put in very early in the building's history. And we felt, given this information and the load that we calculated coming down onto the decorative elements and onto the columns and the behavior of the stone, we felt that we needed to replace and reinstall these new straps, but the new straps would need to fare better and be more sensitive to the stone's materiality. This would help keep original pieces that only had minor cracks from needing full-on replacement. So while the original straps were mortared around the volutes only with no mechanical means of anchorage to the base stone, we decided to mechanically anchor the straps back to the main portion of the column in order for it to grab more of the existing structure that was still in place, should it need to be engaged. Our original design used regularly spaced tapcons around the profile, but we soon abandoned that idea to maintain the integrity of the marble. Instead, we mechanically anchored the straps back to their ends by means of an angled plate that receded into the back profile and would be hidden from view. If the stone were to crack and lead to spalling, the straps would fully engage, and it would engage not only the weight of the volume, but the weight of the column behind it and keep everything in place. We used some volume mock-ups on site to practice the strap installation. You could see that some are on the ground on the image on the left and some are in place on the image on the right. And that helped us refine the detailing of the strap and the installation before installing all of them around the capitals. So once the mock-ups were reviewed and approved and everyone agreed upon the approach, we started prepping the backup stone for replacement installation. The stone volute replacement pieces were anchored back to the stone substrate by a series of stainless steel rods that were epoxied and drilled in and anchored far enough back to grab enough existing stone to keep the replacement pieces in place. Prior to installation, we also conducted on-site Hilti pull tests to make sure that the capacity of the epoxy anchors was suitable for their repair. And here is a finished look. So the last area where we saw significant marble cracking that could have been indicative of a structural concern was at the entablature soffit pieces that were spanning over the volutes. When we were fixing the column capitals, we noticed that almost every soffit panel was cracked and that there were several large fragments already detached and spalled off. So we decided to conduct another probe by removing stonework over the entablature stones to understand first, are the stones self-supporting elements? And secondly, is there any backup structure that's aiding or by contrast hurting them? There's minimal existing documentation in this area. We did find an original section shown on the slide on the left, and it shows that the entablature elements are spanning without, they're full-size stones that are spanning from column to column, and that there's steel above it. And these triangular shapes, we believe, were anchor points of some sort that, connected the steel with the stone, but we weren't sure if they were being used structurally or not. The image on the right is from our probe, and you could see our probe in our black hatched area. That's the stone we removed. And it kind of completes the picture and shows that there's, the steel inside is slightly different, and what we found that I'll present in the next pages are slightly different than the original sections. So this picture shows what we found when we removed two stones in the courses over the columns. The course immediately above the column capital was backed by brick and revealed the spanning stone to be full depth with considerable bearing on the column capitals. It also revealed the course above to be backed by steel, which had significant pack rust, deterioration, and areas of section loss. The probe confirmed that the entablature element was meant to be a self-supporting stone, not meant to hold floor or roof load, but capable of supporting itself. The probe also showed that the spalling was caused by stone anchors. Over here, you can't see it. You can see a spall at the corner because we removed it, but there was stone anchors at each of the ends of the entablature that were installed too close to the exterior face of these entablature pieces. And so we believe that the conditions we were seeing in the cracking and spalling of the entablatures was not a structural condition, because we ran calculations to prove that the entablature could span and support itself. But rather we found that these were just another installation deficiency, in that the metal anchors meant to keep the stones from differentially moving from stones above and to the side of it. They were installed too close to the face of the stone, and water got into them and corroded them and started building that internal pressure that wanted to break and crack the stonework. The larger structural concern we found when we probed was the extent of steel corrosion at these steel lintels meant to hold up the roof and the parapet of the portico. The steel was significantly rusted, with large areas and large and continuous areas of pack rusting, and some areas of complete section loss that you could see in this area where there's a hole through the web on the image on the left. The contractor needed to clean the steel so that accurate measurements could be taken. So this is an image of the conditions assessment we performed, and we took an in-depth assessment of section loss by measuring the clean steel to understand how much steel was actually missing and rusted, and how much steel we could get away with in terms of areas that we needed to repair versus not. So that helped inform our proper repairs and our detailing, which was a plating scheme that we performed on site, because we felt that we could achieve the repair on site without removing and replacing these pieces of steel. Because removing or replacing these pieces of steel would have been a larger constructability issue and shoring problem. And we felt that we did everything in situ. But the larger problem that we had was that these steel lintels are in an exposed condition. They have stone in front of them and they have masonry around them, but water's still going to always get to them. They're not in interior condition. So what do we do with the level of moisture that's going to continually come in behind the stonework and attack the steel, even after we repair them? We were working with the architects to install new flashing, which would divert a majority of that water, but this area would not be 100% waterproof. So after sorting through our options, we, with the support of the Harvard Medical School, decided to install a cathodic protection system as the long-term protection of the steel lintels. The type of system used was an impressed current cathodic protection system. And in this system, anodes are installed within the masonry backup and wired directly to a direct current power source, diverting the corrosivity away from the steel lintels to the sacrificial anode. So in the presence of water, the anodes would corrode instead of our steel lintels. So for our project, a conductive metal mesh ribbon was embedded in a mortar joint sitting on the steel lintel bottom flange to serve as a permanent anode. A rectifier that converts, and I'll show it on the slide right here, a rectifier that converts ordinary line power to a voltage DC to a direct current was located in the attic of the Gordon Hall and still serves as the power source for this system today. So what did we learn from Gordon Hall to be used elsewhere? Locally, we took what we applied at Gordon Hall and used it at the other 4 buildings, because we were seeing that Gordon Hall was one of 5 identical buildings built around this quad at the same time. These buildings appeared to all be suffering from the same moisture and infiltration issues around the stonework exhibited by cracking seen at Gordon Hall. So the phased approach of visual assessment, probing, and testing that we completed at Gordon Hall, we did at the next set of buildings around the campus. We found with our probing and our testing that a lot of the concerns we saw with the stone cracking and spalling were due to detailing issues with thin profiles of stone together with metal attachment points that were too close to the surface. And that together with moisture led to the damages that we saw on the exterior at all of these buildings. So, what can we take away from this story? Namely that the original detailing of the buildings were changed from a brick facade to a stone cladding, and a more in-depth understanding of the cladding materials and their behavior in an exposed environment together with proper detailing in terms of their thickness, anchorage, profile, how recessed the anchorage needs to be from the exterior, that would have alleviated the conditions that ultimately required repair at these buildings. So thank you.
Thanks, Jen. I want to shoehorn one question in here, and I guess it relates to the cathodic protection of the steel, backup steel. Does that extend to the anchors too? Was that an integral protection strategy?
Yeah, so the way cathodic protection is best used is that it's really locally protecting localized elements. So the cathodic protection is meant for those larger wide flanged lintels. The metal anchors were removed and replaced with stainless steel anchors where we needed to. And the whole, the way cathodic protection works successfully is that the steel you're protecting has to be separate from all other steel. So this lintel, because it wasn't part of the major framework of the building and it was far enough away from the metal anchors, it was good that that was a good candidate for cathodic protection, because you have to make sure that the anodes are corroding for particular elements and that your current doesn't get attracted to other metal.
Great, that explains why we don't see these techniques used in new buildings.
Right.
Okay, thank you. I think we should move on to the next question, but we can return with questions for you after the other presenters gone. Thanks.
Our next presenter is Vida Pivo. Vida is a postdoctoral scholar and assistant professor at the University of Michigan, where she specializes in architectural and urban history, as well as environmental studies. Her paper today is Black Concrete Power, the Tuskegee Block and Low Cash Cost Housing. Thanks, Vida.
Thank you so much for the kind introduction and also this opportunity to present with such amazing researchers is fabulous. So I'm just sharing my screen and you can hear me okay and see the presentation?
Yes.
Excellent. Lovely. So this is a little bit different than what you just heard, but I hope there's still overlap in terms of thinking about materials. So in front of you, you see two covers of the popular newspaper, The Negro Farmer, published by the Tuskegee Institute starting in the 1910s to disseminate information about best farming and homemaking practices. The argument was that the introduction of more hygienic ways of living was simple, affordable, and could have significant effects upon the health of the livestock, the family, and community at large. The cover on the right is especially instructive for understanding how Tuskegee communicated the value of farm modernization. It notes, quote, "What good things can a man teach his children in a house like this? What proof of love can he give his wife to outweigh his lack of love, which is shown by having her live in a place like this? What excuse can he give his community for being willing to live in a hut like this? If you live near such a place, ask the man of the house these questions," end quote. The introduction of the modern farmhouse, therefore, did not only provide for individual salvation, respect, and even manhood, but also entailed transformational opportunities for the community at large. To motivate and educate farmers, Tuskegee initiated various programs that taught modern construction techniques. Initially, the older structures were replaced with houses built on concrete or brick foundations, but in these cases, the walls were still constructed of wood. But in the late 1940s, Tuskegee came up with a low cash cost housing program that encouraged Black farmers to employ their own family labor and native materials, along with cement purchased on the commercial market, to modernize their farms and achieve independence. The idea was that concrete would require Black farmers to have little cash on hand to purchase materials, and instead they could utilize water, sand, and gravel available freely on their own farm, creating concrete building blocks over an extended period of time. Concrete could therefore allow Black farmers to achieve the independence they had always hoped for, as one Tuskegee Bank president articulated, quote, "When every farmer in the South shall eat bread from his own fields and meat from his own pastures, and distributed by no creditor and enslaved by no debt, shall sit amid his teeming gardens and orchards and vineyards and dairies and barnyards, then shall be the breaking of the fullness of her day, end quote. What is interesting and unique about this program is its focus on concrete, which as an industry has existed in the service of whiteness, US empire, and capital, a point that I argue in my broader book project. Indeed, the industry's ambition to create permanent and hygienic built environments relied upon assumptions about the stability and coherence of the white body, a category that obviously excluded Black and Brown people. But at Tuskegee, concrete had the potential to enable what geographer Ruth Wilson Gilmore called liberated lifeways. By using their own materials and labor to erect their homes, Black farmers could avoid the white commercial construction and materials market almost entirely. So concrete offered an opportunity to envision Black rural modernity that was not dependent upon the designs and building patterns of the white industry. Here, Gilmore's work is again especially instructive. She notably originated the field of abolitionist geography, which aims to think about how people create life in the midst of violence, from racism and capitalism to settler colonialism. Historian Robin Kelley, too, has argued for a renewed commitment to thinking about the history of marginalized peoples, not through their shared experiences of oppression, but rather their active engagement with place in service of freedom. By focusing on freedom as a place, scholars have made connections to Indigenous knowledge, which has generated new ways to think about the human-non-human divide, conservation, and property relations, all topics of crucial importance for scholars of the built environment. In the context of architecture, I'm interested in understanding how construction materials enabled or disabled freedom making. Were some materials more conducive to liberated ways of living? And what were the limits of these freedoms in the context of the history of capitalism? Before I dig into the low cash cost housing program and its legacies, I want to think about the broader history of concrete and other cementitious materials in the US South. So although concrete was introduced as a perpetually modern material, it was more locally familiar than might appear at first sight. Indeed, in the late 18th and early 19th centuries, enslaved workers employed tabby, a vernacular form of concrete, to construct farm and residential buildings on southern plantations. Tabby concrete, a concoction made by burning oyster shells, crushing and mixing them with sand and water, appeared in Florida, Georgia, and South Carolina. First used by European colonists to construct their communities, the material's laborious manufacture quickly fell into the hands of enslaved workers, who spent a significant portion of their working time collecting oyster shells and acquiring the necessary heat to burn them for lime. The construction process, too, was challenging and involved building substantive wooden formwork into which the tabby mixture was poured. Each layer had to solidify before another could be added. And since the material was thick and chunky, builders relied on its large mass and weight to keep together. When poured to construct agricultural buildings or slave dwellings, the partially burned shells exposed their sharp edges and presented a cold and unwelcoming surface ready to scrape and injure unsuspecting passerby. Although tabby concrete was limited geographically to states bordering key waterways, it nevertheless left a meaningful impact on the local building cultures. Indeed, tabby manufacture and construction was quite different from other construction methods and instead closely resembled domestic forms of farm labor. From scavenging and collecting oyster shells to their burning and mixing with water and other ingredients, and as well as its pouring into wooden molds, making tabby was not unlike cooking. And much like enslaved people's maintenance of gardens that carried familiar medicinal plants, tabby too connected them to their African origins. By some estimates, early forms of tabby were brought to Spain by the North African Moors. Similarly, the manufacture of tabby resembled that of mud brick, created by mixing agricultural soil with leftover straw from the grain harvest, thus further cementing the familiarity of these sibling building traditions. This early form of concrete therefore existed not in isolation, but as part of a constellation of material linkages that connected enslaved people to their geographical and cultural origins. The use of tabby in the US South ended with the 1865 passing of the 13th Amendment to the US Constitution, which abolished involuntary servitude and slavery except as forms as punishment for crime. With the end of slavery, building practices likewise changed to accommodate new financial and labor regimes. And concrete came into the picture to facilitate that shift. However, the connection between tabby and concrete, or the structures of labor that underpinned them both, were never made explicit. Instead, cement industrialists suggested that the two were inherently different media, one rooted in slavery and the other in science and modernity. In other words, the New South would be built not with enslaved, but with carceral labor, not with tabby, but with concrete. Tuskegee students first received their introduction to concrete road construction in 1903, and only 8 years later, they were mastering how to mix, proportion, distribute, and test concrete. An undated photograph of one of such lessons showed students working collaboratively and displaying the mixing process. The young man on the right shoveled sand while the one next to him mixed the material with other ingredients. The remaining students organized the concrete blocks, perhaps stacking them for the construction of columns or foundations. It is notable that the space in which this learning was taking place was not dedicated to concrete work. The large furnace on the left and the adjacent shelves filled with metal gadgets revealed that the room was the Institute's metal workshop. The 5 pupils partaking in this work received minimal supervision and largely directed their own efforts. The students are obviously avoiding any eye contact with the camera, a common trait in photographs that advertise Tuskegee worker skill and subordination, as Anna Goodman and Mara Lucking have argued. Yet their lack of supervision suggests that after learning the concrete trade, these young men would return to their communities and modernize them. The photograph of the concrete classroom reveals even more about Tuskegee Institute's attitudes toward concrete when compared to a documentation of the brick-making classroom. Unlike the borrowed space of the former, the latter was housed in a spacious, modern, and clean-built environment with large windows and lampshades covering light bulbs, an uncommon and impractical luxury. The room was not merely a classroom, but also an exhibition space to showcase the range of skills that Tuskegee imparted upon its students, ranging from various brick binding techniques to decorative columns that integrated various materials for a unique aesthetic effect. Although filled with students busy at work, instructors could nevertheless be easily identified by their professional attire and large project drawings in their hands. The photograph is obviously concerned not with the individual workers, but the group of laborers and their efficiency. A Dixie Brick Company calendar hanging near the window further emphasized that the brick making and laying operation is primarily concerned with business rather than learning. The space too appeared less like a classroom and more like a job site. The elevated balcony with a door to a private room on the second level most significantly recalled the centrality of the factory overseer, or in the case of the US South, the planter surveilling his fields from the porch of the big house. Closely reading the 2 classrooms side by side reveals that while Tuskegee students learned about the importance of concrete for the construction of roads, sidewalks, and foundations, they were not taught to think of it as an especially noble or lucrative material. Indeed, the photograph of the brick masonry classroom was thoughtfully staged to encourage the purchase of locally manufactured brick and labor of Tuskegee students. The image of the concrete classroom, in contrast, sent a different message. With its repurposed classroom and low-tech tools like containers and shovels, the photograph communicated that concrete was accessible to every farmer interested in utilizing this medium. Furthermore, building with concrete was not especially complicated and could be performed one step at a time with the help of family members or close neighbors. Unlike brick construction, which required an army of laborers, concrete work was significantly less elaborate and even domestic. Indeed, workers could fabricate much of the technology they needed for mixing concrete by utilizing basic household equipment. One of the most important Tuskegee programs for popularizing concrete among Black farmers was its 1946 development of low cash cost housing. Perfected over a 10-year period, the project was funded with grants from the General Education Board and developed as an effort to provide modern housing facilities for Black farmers. The first experimental concrete house was built on the campus by Tuskegee students. The project proposed that farmers could erect such structures on their own by utilizing the free labor of their family and locally available materials to manufacture concrete blocks in wintertime. Tuskegee faculty experimented with various possibilities, building houses of timber, rammed earth, and soil cement mixtures. However, these options were problematic because of high cost and requirements for specialized facilities and skilled construction labor. Program leaders finally settled on concrete, mixed by farmers with largely freely available materials. Quote, on most of the eroded cotton farms in the South, deposits of sand and gravel can be found in ditches and creek banks. End quote. So farmers had to purchase cement, of course, at $47 for 50 sacks of cement, which could materialize about 20 blocks per bag. To keep the construction process simple, Tuskegee faculty focused on producing a basic yet well-designed element, the building block, and its formwork. The latter was simple and could be built by, quote, one man with crude carpentry skills, end quote. Indeed, project leaders calculated that one farmer could construct enough wooden forms in one day to hold 100 blocks. He could then mix and pour 10 blocks per hour, and with a month's worth of practice, he could lay 160 blocks in an 8-hour day, or 20 blocks per hour. Tuskegee's concrete block compared well with commercially available alternatives, yet cost significantly less to manufacture. And the only skilled labor that had to be hired was for the laying of the corners, roofing, wiring, plumbing, and chimney building. The project's proposed technique of wall bonding, which included a critical 3-inch airspace, ensured that the blocks remained thin, cheap, and easy to manufacture, yet produced homes that were sturdy and appropriate for the local climate. While the concrete low cash cost housing provided an avenue for an affordable and improved life on the farm, it was by no means free. Indeed, while farmers relied on their families for labor and employed locally sourced materials, they still had to accrue debt to cough up the $2,000 or $2.52 per square foot necessary for the average four-room modern cottage. For many families, these new concrete homes therefore represented years of saving and planning. Photographs documenting educational workshops for concrete low cash cost housing showed rural youngsters learning to lay the concrete blocks using trowels. One image featured 6 young men working on the pouring of concrete blocks into homogeneous formwork, as another man in a trench coat and a hat directed their labor. The workshop participants were situated in an unfamiliar yet domestic looking space with 2 doors leading to the outdoors. Much like earlier photographs of student laborers at Tuskegee, the young men avoided eye contact. Yet with the camera positioned low and close to the ground, it is clear that the viewers were meant to inhabit the bodies of the workers and see clearly what type of work was involved in building low cash cost housing. In other words, farmers from all over the US South, regardless of their literacy, could view the image and understand the processes involved in concrete mixing. And Black farmers were historically used to interpreting visual information. Historian Stephanie Camp has shown that enslaved people half a century earlier decorated their living spaces with abolitionist literature, not because they could read it, but because they interpreted the imagery as a visual representation of the possibilities of freedom. Thanks to the clarity of visual instruction in concrete mixing, farmers could imagine themselves performing this labor and helping their communities embrace this new material of independence. Another telling photograph showed Tuskegee's well-dressed agricultural leaders congregated outdoors, inspecting the formwork and concrete blocks that were created as part of the demonstration. Once again, it is clear that the workshop, along with the manufactured product, were meant to be consumed by Black farmers. Unlike the brick classroom of some years earlier, which displayed and advertised attractive final products to potential white clients, this image showcased an organized but by no means professional workshop. And the concrete blocks were not shown to present a neat and pleasing appearance to illustrate the skills of Tuskegee workers, but instead were stacked vertically to simply provide more ground space for formwork and more concrete pours. Everything about the concrete block, from the construction techniques to the workshops and their organization, addressed the practical needs of Black farmers in their communities. Even the centrally positioned pulley cart anticipated that upon the conclusion of the demonstration, workers will return to the site to move the concrete blocks to continue the manufacturing process. On the interior, low cash cost homes presented environments of unparalleled comfort, marked by individual bedrooms with built-in closets, well-equipped kitchens, and single bathrooms. A heater positioned in the center of the building made sure that the homes were warm in the winter, and covered porches kept them cool in the summer. Large windows included in every room of the house ensured that the residential accommodation was naturally well lit and thus saved energy. With ample land to spread out horizontally, low cash cost homes were always limited to a single level, thus eliminating the additional costs of staircases and overbuilt foundations. Homemakers decorated the new domestic environments by putting to work various discarded papers and fabrics to add color and whimsy to the interior. Since the construction experiment largely focused on structural questions and issues of labor, Tuskegee leaders promised to examine how interiors too could be made cheaper and more efficient through sensible design. They plan to integrate movable and interchangeable walls, compact furniture and storage units, and new panel material for floors and ceiling. By constructing their own concrete housing, Black farmers revealed the liberatory potential of the material. Indeed, concrete had the potential to be an empowering tool of self-sufficiency and independence. Sociologist Monica White has written about how agricultural resistance inspired the Black freedom movement. She traced how agricultural work for enslaved Africans created a connection to national origins and cultural traditions. Many of these men and women maintained their own gardens to provide subsistence, but also to preserve their personal histories and memories. Slave gardens thus can be understood as, quote, a strategy of resistance to a corrupt system and an effort to create food security, end quote. Concrete too offered the opportunity to resist construction practices that were regulated by white power. Instead of relying on lumber, brick, or other materials procured by white manufacturers, Black farmers could collect their own materials independently and mix them together with cement to manufacture their own construction elements. The new approach thus enabled the modern rural farm to challenge its associations to oppression and instead create conditions for sustained collective struggle and community building. As Tuskegee's experiments with concrete block construction expanded opportunities for Black farmers, they also drew local and national media attention. Indeed, the projects attracted not only coverage, but also financial support from wide individualist institutions like the Southern Research Foundation. The US Housing and Home Finance Agency also noted that low cash cost housing was not merely an experiment, but an engine for transforming the construction of rural and suburban dwellings in the US South due to concrete's capacity to resist house fires. And the ripple effects of this new mode of rural modernization were felt not only in the US South, but also the global South. Both Tuskegee and the federal government entertained the idea of using the low cash cost method to construct housing in the developing world as part of the President Harry S. Truman's Point 4 program. In 1950, the Federal Housing and Home Finance Agency granted Tuskegee a 2-year, $60,000 research contract to examine cooperative construction labor and peg down the technical aspects of the housing plan. And a year later, the Paley Commission's 1952 report, Resources for Freedom, identified the importance of the concrete block, stating that, quote, "It is one of the most spectacular developments of the last few decades," end quote. While enthusiasm for low cash cost housing was rampant, the building system did not become as widespread as initially imagined. Nevertheless, this moment in construction history presents an opportunity to consider what a disinvestment from oppressive labor regimes might look like and what it might mean to think about freedom as a place. Thank you.
Thanks, Vita. We have a question from the audience, but I'm going to hold it till after Rachel's presentation. That was awesome.
Our final presenter is Rachel Cruz. Rachel is a research scientist in the UK. She holds a PhD in structural engineering from Imperial College London. And in addition to her research and teaching, she serves as technical editor of the Architectural Research Quarterly. Her presentation is entitled "The 300-Meter Eiffel Tower, the Role of a Structural Principle." Rachel?
Thanks very much, Marissa. I'm just sharing my screen. Hopefully you can all see the presentation.
We do.
Brilliant. Thank you very much for the introduction, and thank you very much to the Construction History Society of America for this opportunity and for my co-presenters for such interesting talks. My talk is going to be perhaps obviously about the Eiffel Tower and specifically looking at the design process of the Eiffel Tower. This is a project that I undertook while working at Sheffield University and Loughborough University. And I currently work as part of a new regulator in the UK to look after high-rise buildings called the Building Safety Regulator. This came out of the Grenfell tragedy, which happened in 2017, which you might have seen in the news. Obviously, it's important for me to say that this project isn't a reflection of the new regulator's view on the structural performance of the Eiffel Tower. It is a personal piece of research. So to start off with, I think it's important to say that probably the Eiffel Tower doesn't need an introduction, mostly because of its iconic profile. But at the time of its completion, it was a really unique building because it was the tallest structure that was ever built. Gustave Eiffel is often linked with the tower because it's the tower's namesake, and he's often cited as its designer. But he actually had more of a role of promoter and persuader to get it built as the entrance to the 1889 Paris World Fair. And his employees in his engineering company were actually responsible for the initial design. So Gustave Eiffel had a number of challenges in getting to convince the public, engineers and politicians that the tower was feasible. And one of the most important ones was demonstrating that the tower could resist wind loads because of its height at 300 meters tall. It was 2 times the tallest building that had ever been built, which was the Washington Monument previously. And the second challenge that Eiffel had was to persuade people that it was a suitable addition to Paris, because Paris was then the center of the Beaux-Arts movement. Eiffel's approach to this was to link the technical issue of supporting the wind load to the aesthetic of the design by stating that the unusual curve of the tower was determined by the wind loads acting on it to effectively resist them. Eiffel, in his initial promotional presentation in 1885, which was to the French Society of Civil Engineers, set out this structural principle, and he set it out again in the final publication he made on the tower in 1900s. This publication was 11 years after the tower was constructed, and he wrote it principally in order to stop it from being pulled down. So this structural principle runs all the way through the design process of the tower. It doesn't ever change, so it's seemingly a kind of constant throughout the tower's design and construction. And I'm going to try and explain the structural principle to you, and in order to understand it, I'm going to start with a very basic vertical truss experiencing a horizontal or wind load. Here you can see on this truss, you've got some vertical elements and some horizontal elements, and they're connected together by connections that rotate, that can rotate. So that means that when the wind load is applied, the structure collapses or what's called racks. Obviously, we don't want that to happen to any structure, and the options to prevent it from happening are firstly what's called a brace truss, where you include braces or diagonals in between the vertical and horizontal elements to prevent the racking. And the second is to have what's called a rigid truss, where you make the connections between the horizontal and vertical elements strong enough, rigid enough to stop the rotation happening. So you create what are called rigid connections. So Eiffel describes the principle in the two publications that I've cited. And basically what he's saying is that in order to remove the need to have bracing or diagonal bars, you can give a curvature to what he's calling the uprights, and the uprights are the elements that perhaps were once vertical but have now been inclined at an angle. And he's saying that if you take a section through these uprights at a certain point, so if we take a line between M and N, then the tangent to the curve of these uprights at that point should intersect with the resultant of the wind force that acts on the surface area of the truss above the section line MN. So it's quite a complicated principle, but basically what this means is the uprights act as both the elements that take the vertical loads down to the ground, but they also act as the braces because they're angled. So this is Eiffel's notion of efficiency. He's reducing the need to have additional braces as you might have in a typical brace truss. The reason for the intersection of the resultant wind load and the tangent of the legs at points up the tower ensures that all the elements only carry tension and compression, and they don't go into bending. Tension and compression are much more efficient ways of carrying load. And so in this way also, Eiffel was ensuring through this principle, he proposed an efficient structure to carry these wind loads down to the ground. In practice, what this means, and this isn't noted by Eiffel anywhere or indeed by his engineers, is that what you've got to do is to start your design at the top of the tower and gradually work your way down, taking sections through the tower, getting lower and lower. So if we start with the section line MN, what we need to then do is define what the surface area of the tower is that is going to be interacting with the wind loads above the line MN. And we need to multiply that by the wind pressure above the section line MN to get our forces and any safety factors that you want to include in that. And that will help us determine the location of the resultant wind force above the section line MN. This in turn is going to define for us the tangent of the angle of the legs at this section line. And if we take that just a step further, those tangents are going to define the surface area above the next section line that comes below it. So the tangent lines are, if you like, defining the shape of the tower above the point that you're considering. And so it's a cyclical design process where you have to kind of just work your way down the tower to generate, if you like, the shape of the tower in response to the position of the resultant wind loads that you're getting at each position that you consider. This is a complex process, and I'll talk a little bit about why it's important to sort of understand what this principle actually means in terms of the design process. Hopefully you can see that it really is a principle that has to control the whole design process of the tower in order for it to be used, in order for it to work. Hopefully it's obvious that Eiffel's structural principle then needs the knowledge of the wind pressure up at the height of the tower, 300 meters, and also how the wind would interact with the tower. It's sort of interesting to point out that it's an open lattice work, which is very different from buildings that have preceded it. And so typically, like the Washington Monument, you've got a solid brick surface that was catching the wind. This is very, very different. And Eiffel admits to the French Society of Civil Engineers in 1885 that he, A, doesn't know what the effects of the wind will be in terms of how big it might be. And he doesn't know how the wind is going to interact with the tower. Now, to be fair to Eiffel, this is because nobody could reach 300 meters to measure the wind pressure or to measure the interaction with surfaces, different types of surfaces at this height. So it's not because Eiffel's not on top of his subject, it's just because of the timing and the advances of technology at that point in time. But this statement from Eiffel, it raises a really important question, which is, if the structural principle is used to define the curve of the tower, how are you going to use it if you don't know how the wind will interact with the tower? And in order to answer that question, I located the existing documents that could help detail the use of the structural principle during the design of the Eiffel Tower. And these were listed here, and they include elevations of the tower that were published, as well as structural calculations that have been preserved over time. These sit between the initial proposal for the tower, which happened in 1884, its completion, and its final design, which was documented in Eiffel's final publication in 1900. To underline the lack of knowledge about the wind loads in this period, the calculations between those two periods, 1884 and 1900, showed three different wind pressure distributions were considered. The first, case 1, varies from 200 kilos per meter squared to 400 kilos per meter squared. And the second one is a uniform wind distribution, which is 300 kilos per meter squared all the way up the tower. So this is the height of the tower going up to 300 meters at the top. And the third case is a uniform wind distribution 2 of 400 kilos per meter squared. Also, you can see a variation in the way in which the surface area is being defined at the tower. So this is about the interaction of the wind with the surface of the open lattice work. You can see here that areas that once were assumed to be a solid area that would catch the wind have now been sort of converted into a much more detailed understanding of individual surfaces within the truss area. And also, finally, you can see hopefully from this graph a variation of safety factors during that period too, with very little indication from the documents as to why those safety factors were changing. The initial proposal for the 300-meter tower was made by an engineer in Gustav's company called Maurice Koechlin. And this is the first, what's thought to be the first drawing ever made of the tower from 1884. The drawing shows fundamentally a piece of engineering, and there's very little ornament or decoration going on. But what is worthwhile pointing out is you can see the curved uprights and the horizontal trusses connecting with no kind of bracing between the levels. You've just got connections between the uprights and the horizontals. So it's encouraging to sort of think this is why the structural principle is needed. Later in this year, we have preserved in ETH Zurich's archives some calculations which are by Koechlin, but also his colleague Emile Nuyer, which are looking at the loading on the tower. And they take into consideration a particular wind loading case, which is the uniform 400 kilos per meter squared. However, these calculations, when you look through them, they actually don't adhere to the structural principle that Eiffel published. They don't demonstrate that it's been used at all. And what I tried to do with this set of calculations is then take the areas, the surface areas indicated in the calculations and the wind loading case, and calculate the profile that I thought should have been generated by the structural principle. And that's indicated by the blue circles, and principle 3 at the bottom there is the key. And I compared that with a measurement of the profile of this elevation. Now, whilst there's no actual link between the calculations and the elevations, you can see a direct relationship by the number of panels and the way in which the truss is designed in the calculations compared to the elevation. So there are similarities across there, and I thought it'd be interesting to compare the two to see how they sort of work together. The little blue crosses are the measured profile from the elevation, and you can see that broadly there is a similarity in the shape, but even considering the errors that might have been incurred in terms of measuring that profile of the tower, there's actually a significant difference between the two, with a maximum of 3 meters within this half profile going up to the top of the tower. And this is the base of the tower at the bottom. So it's actually very unlikely, based on what you can see in the calculations and making this comparison, that the structural principle was actually being used to define the shape of this elevation. Following Koechlin's proposal, Eiffel liked the design so much that he backed the design and asked an architect, Stephen Silvestre, to come on board the project. And the result of that was a much more decorative Beaux-Arts elevation. This is an engraving that was published initially in the magazine La France in 1884, late 1884. But it was also used at the front of the document of Eiffel's presentation to the French Society of Civil Engineers in 1885. Also in this document of his presentation is a set of calculations. And this time, these calculations show the use of the structural principle. In fact, they show very clearly the generation of 2 different profiles that are possible for the Eiffel Tower. One, considering the varying load case 1 from 200 kilos per meter squared to 400 kilos per meter squared. And the second case, which is the uniform load case of 300 kilos per meter squared. And you can see case 1 as principle 1 and case 2 as principle 2. So the yellow circles and triangles are forming a profile based on the data from his calculations and using the structural principle to generate those data points. And the crosses, again, are the measured profile from the elevation. And hopefully it's very obvious from that graph that there's a big difference between the structural principles that are very clearly shown inside the documents compared with the cover image that he's using to essentially market the project. And the maximum difference is about 8 meters. In June 1886, the Eiffel Tower was declared the winner of a competition to be the entrance of the 1889 Paris World Fair. And this was really down to Eiffel's persuasive powers. It was no surprise because the brief of the competition was pretty much the description of the tower he had presented in 1885. His company then started out on more detailed construction drawings, including the one that I'm showing here. And this is particularly interesting because it sets out a way to approximate the surface areas that are going to be hit or interacting with the wind loads. Now, for this particular drawing, because there weren't any assumed wind pressures given to multiply with the surface area to start thinking about forces, what I did was I took all three cases in loading cases and created three different profiles, the circle, the triangle and the square sets of data. You can see that the circle profile is very different from the triangle and the square, which are the two uniform loading cases. So the circle is the varying loading case. And what is actually probably important to point out is that the two uniform loading cases are actually identical. The profiles are identical. And what this sort of demonstrates is actually the magnitude of the wind is not important in the way in which the profile is defined through this particular structural principle, but the distribution is important. What I also did, as before, is to measure the profile of this elevation and convert that into another set of data on this graph, which is the little red crosses. And hopefully you can see that actually the measured profile matches up very nicely with the profile generated through the structural principle for the uniform loading cases. In January 1887, Eiffel signed the contract to start the tower's construction. The discussions about the contract had gone on for a very long time. So it was actually whilst the foundations were being built that the contract was signed. And the following elevation is part of the contract, a sort of an image of what they're hoping will be built or agreeing will be built. It hasn't got any calculations, but I thought it would be worth comparing it with the profiles from the 1886 diagram showing the surfaces presented to the wind, so the previous drawing I was talking about. And if we make measurements from the tower and create a half profile, hopefully you can see the little green crosses are coinciding pretty nicely with the uniform loading cases, which I've collapsed because they are identical into just one set of data, which is the green circles. And you can see that it's very different from the varying load case. So what this is showing us is this is the first time where we've got a kind of a coinciding of the aesthetics of the tower matching what we think we should have if we follow through the structural principle that we're being told is used to design the tower. The Eiffel Tower is supposed to be a temporary structure, and in 1900s people were starting to discuss taking it down, and Eiffel's response was to publish what he described as the final design of the tower, and that was complete with the description of the structural principle I'm talking about, construction drawings and structural calculations. And what's really interesting about the structural calculations is rather than show how the structural principle was used to define the curve of the tower, the calculations showed the difference between the actual designed profile of the tower and the profile that should have been generated by the structural principle. And they show how structurally they've had to adjust for this in order to ensure the structural integrity of the tower. So there's sort of very obvious admission that the principle isn't generating the final profile of the tower. And in fact, if you look at the final elevation in this book, you can kind of see why, because the upper part of the tower is effectively a braced truss. If you think back to Koechling's initial design, you had gaps between the horizontal trusses and the uprights. But for the upper part of the truss, this is all filled in with bracing. So effectively, this is a braced truss, and there is no need for using the structural principle to make this stand up. And in fact, if you look at the calculations, they are designing a braced truss. And for the bottom part of the tower, whilst we haven't got any bracing between the uprights and the horizontals, what we have got is very clear indications in the structural calculations that the connections between the horizontal trusses and the uprights are being designed as rigid. So effectively, the bottom of this tower was designed as a rigid truss. And so again, the structural principle is not structurally needed. So taking the final tower's profile, this one, and measuring it again and comparing it against what should have come out of the structural principle, in this case for all three loading cases, you can actually see that for the uniform loading cases, principles 2 and 3 there, it's a pretty good fit. But there are still actually significant differences, particularly at the top of the tower. So that sort of, if you like, confirms what Eiffel is doing in some of the calculations he's presenting by adjusting for the difference between what the shape actually is and what the structural principle is telling us it should be. If we group together all of these elevations that I've shown, hopefully you can see in the graph that these two early elevations, both from 1884, they're blue and yellow on this graph, and hopefully you can see that it's a much steeper curve in those early days than we end up with in the last three designs, which are sort of all clustered down here and much more concave. So initially, the designs you have are very divergent from the aesthetic projections of what the tower should be compared to the structural calculations. Then we have a really strange step change in shape. And the shape actually is very similar between all three periods in the design process here. It doesn't change very much. There are little differences though. And what that does is it sort of raises the question why the final design doesn't actually match with the profile based and generated on the structural principle. And this could well be because of the complex process of generating the profile based on the structural principle. In other words, one change to the surface area in the tower would require a regeneration of the profile below that change using the structural principle. And perhaps there was a point in time somewhere in this design process when they didn't want to go through that loop of regenerating the curve, and they were just adjusting slightly for additional or removal of surface areas as the design got refined and finalized. So the design development on the tower, on the face of it, it tells a story of a struggle between perhaps an aesthetic look of a tower and achieving this structural principle and realizing the structural principle. The use of the structural principle seemingly had a lot of control over the design process, but equally there are moments in time where Eiffel uses it as an excuse for the aesthetic of the profile of the tower. There's a very famous letter that was written from artists in Paris saying how horrific the tower was and they didn't want it to be built. And Eiffel, true to form, replies stating this principle and using the structural principle as an excuse for the way the tower looked. But the reality is that given the lack of knowledge of wind loads and how they would interact with the tower, the profiles generated on structural principles were massively subjective because they didn't know the wind loads, they didn't know how the wind would interact with the tower. And even more importantly, ultimately, if the final structural design of the tower published in 1900s is true, its structure is designed to resist wind loads completely without the need of the structural principle. So at least for the final design, the principle is seemingly irrelevant. And this raises really interesting questions over whether the profile was chosen because of its aesthetics, or was it a result of engineering assumptions, or perhaps the truth lies somewhere between the two. And there's slight aesthetic choice going on in terms of the subjectiveness of the values being put in to the structural principle. And perhaps it was something that, at least initially, after that change in 1886, defined the shape, the initial shape moving forward of the tower. Thank you very much. That's the end of my presentation.
Great, thank you, Rachel. That was really interesting. I want to relay a question from our chat, and it has to do with the use of iron versus steel. Nick, who posed this question, mentions that Eiffel had used iron on previous structures, and justified it based on the idea that it was better in tension and compression than steel. Did you come across this in any of your work?
A little bit. Sorry, there's some fireworks going off in the background. It's bonfire night here, so apologies for that. Yes, so there was actually quite a conversation that Eiffel had with other engineers about why he wasn't going to use steel. And I think really probably the truth of it is he had built iron structures successfully up to that point, and that's what he understood. And I think that a lot of what you see sort of coming out of these design processes is that he's building on prior knowledge and prior experience, because he's having to make assumptions because the knowledge isn't there yet. And so you can kind of feel that it's a bit of security that he knows what this material is going to do, what it's capable of, even though perhaps we can, with hindsight, look back on it and say, well, come on, steel would have been more efficient.
Thanks. A question that I have has to do with costs and the idea that maybe Eiffel wasn't motivated by reducing the amount of material used. I mean, his end design is much less efficient materially than the initial concept. That is subordinate. Has that been part of your, and wonder if that might play into some of the changes?
I think I haven't sort of stumbled across an awful lot of him dealing with costs in the documents I've been looking at. But what I have stumbled across is an analysis of the tower. I can't remember by the author who it was, but it was a conference paper. And he had looked at the tower and decided that it was 4 times more redundant than it needed to be. So I think the sort of pressure on costs probably wasn't as immediate as it would be nowadays. And I think that Eiffel felt very much that this tower was a flagship. And indeed, you know, he's synonymous with it. And it was probably the pinnacle of his career, if we look back on it. Indeed, he ended up in the tower after his Panama Canal crisis, measuring wind loads. So he completed the circle. He knew he didn't know what the wind loads were, and he came back and he measured them to see what they were. But I couldn't comment on sort of specific things to do with the cost of the tower. That's
fine. Question that someone from Andy has posed. He says, oh, I'm sorry, I jumped at Lee. As laser illumination was applied, was some unneeded brazing removed? I'm not sure where this fits in the time continuum.
It's not something I'm aware of. I guess there are many sort of things that have happened to the Eiffel Tower since its, final design or final construction. And what would be super interesting would be to measure, like Jenna was showing with her data point clouds, the actual profile now. Of course, it's not just wind loads that the tower has been designed to cope with. It's got to deal with thermal changes. So it being a lump of metal, if you've got the sun on one side, it's going to expand compared to the cooler side that's in the shade. So there's a lot of really interesting things that would be, I think, interesting to find out about the tower now, in terms of what loads it's actually experiencing versus the sort of theoretical ones that I've been messing about with.
Thanks. I want to relay one more question to your talk before doubling back to the other presenters. And this is that Andy says, I've seen drafters use graphical methods for structural design. Were the methods used by Eiffel's team strictly numerical or a blend? I wanted to add models into the equation. I mean, we test wind loads on in chambers. But couldn't a model be built and we would exert some pressure to that model as well as?
Well, that's true, but I suppose the issue would be in building models, what pressure do you apply to it? And I think people were in such a state of unknown that wasn't something that happened. What the original question was, sorry, can you remind me?
Oh, it says that I've seen, was there a hybrid of like diagrams and math?
Yes. So all the calculations were static graphics, which was absolute pleasure to look through, I have to say. Took ages, but I'm really enjoying working through them. And of course, you can sort of see why the principle came about, because the way that you're drawing the forces and therefore kind of drawing the members that carry the forces, you're sort of, if you like, generating the shape of whatever you're designing through the forces. And so the link between the shape and the structural workings is, you know, really, really close in the way in which he describes how the tower works originally.
This is absolutely fascinating. Vita, I want to relay a question to you from the audience. Dennis asks, in the construction of Boston's Wachusett Aqueduct, and that might be proper pronunciation, I'm not sure, black crews were brought from the South. It was said, it was said specifically for mass concrete work, although they also performed some other tasks. Although they may have represented cheap labor, Italian immigrants were also used for seemingly less skilled land clearing tasks. Are you aware of such use of black workers specifically for concrete work? And this idea of having a
Thanks so much for I didn't know the specific case you mentioned, but that was pretty common, and mostly I think to break strikes, black workers were used in that context. But it makes sense because part of my research looks at cement manufacture in the US South, and that was a really interesting and attractive region for industrialists because there were all of these agricultural workers who just had great capacity to kind of sustain long hours and dangerous work conditions. So the cement industry expanded to Alabama and Mississippi for that reason. So it makes sense that they would have brought back workers with some knowledge of this material and construction principles in the late 19th century.
Thanks. Mohammed asks, could you expand more on the impacts of the Tuskegee concrete housing experiments on similar construction experiments in the global South? Similar methods of construction, CMU housing, have become incredibly popular across regions like Sub-Saharan Africa and South Asia. And I never realized that it might have roots in foreign investment and aid and programming.
So in my research, I look at the construction of cement factories as well, cement plants in Africa and the Middle East too, as part of aid programs. And this was often connected to oil extraction. So to extract oil, you need to have roads, and to have roads, you need to have cement. But in terms of Tuskegee, what is interesting is that Tuskegee had been participating in different kind of agricultural exchange programs in West Africa and sharing kind of practices for growing cotton with African farmers as a way to relieve poverty and improve kind of efficiency. So it makes sense that Tuskegee would then consider concrete to be an attractive option. And like I mentioned, I'm not entirely sure to what degree this really materialized, but I think from the US kind of aid perspective, this was an attractive option because this is, the 1950s, kind of global decolonization is underway, and I think this was a kind of soft power move to spread US influence in US kind of material and construction cultures. But definitely a super interesting space for kind of global exchange of construction techniques.
Thanks, Vita. There's a couple of questions more related to your topic in the Q&A section, if you could.
Sure, yeah.
I want to just relay a question that Jenna has already replied to, but share with the audience. And the question has to do with the antidotes. Are sacrificial antidotes really permanent, or do they have a lifespan? If so, how long? I think it's interesting because this is a preservation project, approximately 100 years after original construction. So looking forward.
Yeah, so I did answer it in that the anodes corrode at a very, very slow rate. And so the service life of these systems are still being studied because some of the earliest installations are still within our generation. But they are at a minimum 25 to 30 years service life. And usually it's the power source, whether the owner abandons it for a different power source or the building changes ownership and the new owner doesn't want to keep supplying the power source. That's usually the thing that gets services first. So it's anticipated that if the owner keeps up with the power source, the anodes have, decades of a life ahead of it.
Thank you. We're approaching the half-hour mark. I appreciate it that panelists have stayed with us so long. I'm not going to forward any more questions, but if Risa, or if you have anything you want to ask, or panelists would like to ask each other, if not, we'll convene. Thanks. Well, thank you very much. This was absolutely a treat. Look forward to hearing further developments on this research. I'd like to meet everybody at the conference in Atlanta. Please feel free to submit a similar paper topic. And we record this and we put it on our website. So look for it there. And I think Risa, any parting thoughts?
Just reiterating the thanks to all of our panelists. And yes, we would love to have you join us at our upcoming conference, and to all of those who joined in the webinar. Thank you.
Thank you.
Thank you for organizing.
Yes, thank you ever so much. It's been super interesting to hear everybody's presentations.
Melanie.